Okay, I'm going to try a little experiment here now. I'm going to grab some Golang blog articles and actually try them out in code. And I'm going to try and just stick to using the Go playground for this. This is an older article. This is 2014, so it probably doesn't go into some of the things like using contexts and some of the more modern Golang principles, but I am always interested in concurrency stuff, so I think this might be an interesting exercise to go through. So what I'm going to do is I'm going to go through this article. Sorry, but I'm going to read some of it out loud as I'm going through it, and then we're actually going to try and run it and see what happens and try and learn from it. It's kind of a long article. I may not get it all done the first go around. I'll try and keep this video short, but let's see what happens. So, like I mentioned, I'm trying to focus on concurrency idioms for Golang and patterns, even though, patterns is a bad word. Commonly used ways of doing concurrency in Golang, more idiomatic to Golang's features. So let's just see. Golang's concurrency primitives make it easy to construct streaming data pipelines and make efficient use of I/O and multiple CPUs. Good. This article presents examples of such pipelines, highlights subtleties that arise from the operations when operations failure, and introduces techniques for dealing with failures cleanly. What is a pipeline? Okay, so I think we have a pretty good idea for what a pipeline is. Just one of many concurrent programs, a set of stages connected by channels, where each stage is a group of Go routines running the same function. At each stage, the Go routines receive input from upstream via inbound channels, perform some function on that data, producing new values, send values downstream via outbound channels. Each stage has any number of inbound and outbound channels, okay, except that the first and last stages, which only have outbound and inbound. The first and last, which only have outbound and inbound channels respectively. The first channel is sometimes called a source and producer. The last is the sink or the consumer, right? So pretty standard definitions. So let's begin with an example. I will present more realistic. So this is, consider a pipeline with 3 stages. The first stage, gen, is a function that converts a list of integers to a channel and then emits the integers in the list. The gen function starts a routine that sends the integers on a channel and then closes the channel when all the values have been sent. Okay, so let's just grab this, throw it into our little program over here. This is just a standard Go playground default. The second stage, square, receives the integers from a channel and returns a channel that emits. So it receives the integers from a channel and returns a channel that emits the square of each received integer. After the inbound channel is closed and this stage has sent all the values downstream, it closes the outbound channel. Okay, so let's grab that. The main function sets the pipeline, runs the final stage. It receives values from the second stage and prints each one until the channel is closed. All right, so we've already got a main, so we can just grab this. And I've got to get used to this editor. Ooh. Ooh, this is going to be painful. Oh my god. Okay. Maybe I might want to switch this over already. I usually use VS Code. I just thought, oh, this will just be easier. I don't want to have to set this up in this box. But let's see what happens. All right, so let's just try and run that. Oh, I can just format it. That's what I should have done. I don't use this enough. Format. There, much better. Okay, so let's see what's happening here. So we're going to generate from 2 to 3. I think it's 2 to 3, or maybe it's starting at 2. Then we're going to square this channel. So this is going to give us a channel. And we're going to square the results of that channel. And then we're going to get that. And then we're going to take the input from that channel and output it. And it's doing it twice. 4, 9. So maybe these are 2 different. Let's just have a look here. Okay, so it's just list of integers, not actually as a list, but as a set of parameters, and it returns an outbound channel of ints. So we make the channel of ints, and then we do this in parallel, but we return the channel. So this is going to still be running and populating the channel. So blah, 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 stuff it in there, close out the channel. Okay. This one we're going to take an input channel and we're going to give another channel back. So same sort of deal, make a channel, start this straight away, take the value and square it. Okay, so pretty cut and dry. So now we should get 4 and we should get 9, right? Which we do. Cool. Right, that makes sense so far. Where could that go wrong? So since square has the same type for the inbound and outbound channels, we can compose any number of compose it any number of times. We can also rewrite main. Now, actually, that's kind of a. Let's have a look at that for a second. Okay, yeah. So we're not doing this. This is only going to take one value out of it, and this is going to take one value out of it, right? Since square has the same type for inbound and outbound channels, we can compose it any number of times. We can also rewrite main as a range. Okay, that's what I was just wondering just then. So the range of that channel, and that takes a channel. Okay, interesting. So we're going to generate these two things. We're going to square them. So that's going to give us our 4 and 9. And then we're going to square that again. And that'll give us our 16 and 81. Let's just try that. Make sure that's still cool. And format. Oh. Format. Run. Okay. 16 and 81. Good. Multiple functions can read from the same channel until the channel is closed. This is called fan out. This provides a way to distribute work amongst a group of workers to parallelize CPU use and I/O. A function can read from multiple inputs and proceed until they are all closed by multiplexing the input channel onto a single channel that's closed when all the inputs are closed. This is called fan in. Okay. We can change our pipeline to run 2 instances of square, each reading from the same input channel. We introduce a new function merge to fan in the results. Okay, so gen is going to be the same. It's going to fill up that channel. Now we make 2 channels, which is the first one is going to take that. The second one's going to take that. So that's going to give us our 4 and our 9. And then we're going to have this new mysterious merge function that's going to take these 2 channels, probably pop one off of each channel, and then print the results. So in this case, we're going to have 2 and 9. And they're both reading from the same channel. No, they are both reading from the same channel. So they both get 4 and then 9, or 9 and 4, of course, because depending on how the concurrency works. So let's just try that just to double check. Oh, of course we need our merge function. So let's grab that. This has got some interesting stuff in it, and we'll come back to that and figure it out. Let's grab that, format, run, sync we need. And let's run that. Okay, 4, 9. We run it again. 4, 9, 4, 9. It's probably cached. But it could probably be 9 and 4. Well, let's just see what this thing does first. So the merge function converts a list of channels. Okay, so that's going to be our list of channels into a single channel by starting a go routine for each inbound channel that copies the values to a sole outbound channel. All right. Once all the output go routines have been started, merge starts one more go routine to close the outbound channel after all sends in that channel are done. Sends on a closed channel panic, right? So it's important to ensure all sends are done before calling close. And we're going to use a wait group for that, which makes sense. Okay, so we've got our wait group, we've got our out channel, which is also ints. Start an output go routine for each input channel in CS, which is right here. Output copies values from C to out until C is closed, and then calls wait group done. Okay, which makes sense. So, take a value, take an incoming channel of ints, and then run over those and spit them to the output channel, and then say we're done. Okay, so that's just what this function is. We've got n items coming in, so our wait group is set up. And now we're going to fire off each of these. Okay, so that's the interesting part there, is that multiple readers get the same value. I'm not sure about that. Start a go routine, close out once all the output ones are done. So this is going to launch, and then it's just going to fall through. So this is still running by the time it gets here. So now we've got this new function that's going, and it's going to, we know that we can wait on this many things. All right, this is our wait group done is here. So we're going to wait for all those things to finish, and then we'll close our output channel up here. And then we're going to return this. So this can get sent back straight away. So no one's blocking here. This is, as soon as we call merge, this thing is going to whip right through it and return, so that our main picks it up right here. And then everything is going to be running in Go threads, basically Go routines behind the scenes. Okay, so that's pretty cut and dry. Now, there's a pattern to our pipeline functions. Stages close their outbound channels when all the send operations are done. Stages keep receiving values from inbound channels until those channels are closed. Right, so they keep receiving, yeah. So it's going to keep receiving on this until that channel is closed. This pattern allows each receiving stage to be written as a range loop and ensures that all Go routines exit once all values have been successfully sent downstream. But in real pipelines, stages don't always receive all the inbound values. Sometimes, this is by design, the receiver may only need a subset of values to make progress. More often, a stage exits early because an inbound value represents an error in an earlier stage. In either case, the receiver should not have to wait for the remaining values to arrive. We may want earlier stages to stop producing values that later stages don't need. Okay? In our example pipeline, if a stage fails to consume all the inbound values, the Go routines attempting to send those values will block indefinitely. So, for example, consume the first value from the output. Okay, so we get our channel, we grab the first value, and then we bail out. Since we didn't receive the second value from out, one of the output Go routines is hung attempting to send it. Correct. This is a resource leak. Go routines consume memory and runtime resources, and heap references in Go routines are kept until the data, to keep the data from being garbage collected. Go routines are not garbage collected, they must exit on their own. Correct. We need to arrange the upstream stages of our pipeline to exit even when a downstream stage failed to receive all the inbound values. One way to do this is to change the outbound channel to have a buffer. A buffer can hold a fixed number of values. Send operations complete immediately if there's room in the buffer. Okay, so now we're going to make this into a buffer channel. So, we've got room for 2 in here. Add that, and and this one's going to block. Okay, makes sense. Right, so this is just a little queue, and we've only got a size of 2 in it, so these two can fill it up, and this one's going to block until room is made, which means it's somewhat consumed out of this channel. So when the number of values to be sent is known at channel creation time, a buffer can simplify the code. For example, we can rewrite. My first gut reaction is that this is making things a little bit more lockstep, but I'm sure that's the direction they're going with this. When the number of values to be written is, you create a buffer, right? So, for example, we can rewrite gen to copy the list of integers into a buffer channel and avoid creating a new Go routine. So we know how many integers we want to have because we know this. So we make a channel that big, and then we just pump it right in there. Close it and return it. Okay, so we're not going to be doing any more publishing on here, so that's fine. Returning to the blocked Go routines in our pipeline, we might consider adding a buffer to the output channel, returned by merge. Okay, so we know how many channels we have coming in. And we're only going to make it 1 deep. While this fixes the blocked Go routine in this program, this is bad code. The choice of a buffer of 1 here depends on knowing the number of values merge will receive and the number of values downstream changes will consume. This is fragile. If we pass an additional value to gen, or if the downstream stage reads any fewer values, we will again have block Go routines. Yes, for sure. So ideally this would be either big enough to do it, or it can close out properly. So when main decides to exit without receiving all the values from out, it must tell the Go routines in the upstream stages to abandon the values they're trying to send. It does so by sending values on the channel called done. Okay, so we're going to make a new channel called done, and this is going to be our signaling channel. And it sends 2 values since there are potentially 2 block senders. Okay. So in this case, we're going to create our input. We've got our 2 channels from the output. This is our done channel because we've got 2 channels. We're going to do a merge with our done channel being first, and print our value. And then we'll put in a dummy value into here to tell them to bail out. All right, so let's grab that first and make the other changes as we need. So in this case, we're going to switch all this to this new code. And we're going to change our Go routine setup here. And this is basically up to the output function for merge. Okay, so let's see what we did here different. Oh, I think it also takes a different parameter. It also takes a done, right? It would have to. Okay. So in this case, before we were just grabbing 1 from each channel here. Okay, let's have a look here. Start an output Go routine for each input channel in CS. Output copies values from C to out until C is closed, or it receives a value from done. And then it calls workgroup done. Right, so if we have something pending in the out channel, we'll do it. And if we have something here, we'll do it. Well, basically we'll I'm looking for a break, but I'm not seeing a break. Okay? And then the rest is all the same. Yeah, so we're just printing the 1 out. So in this case now, we've got our 2 outputs and are done. So we grab 1 value and then we bail out. And this is our signal back. I need to look that up. All right, so select channel. Go select lets you wait on multiple channel operations. Combining Go routines and channels with a select is a power feature to Go, right? Blah, 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 blah. Right, so if we've got something here, then do it. If we got something here, otherwise. Each channel will receive a value after some amount of time to simulate, for example, blocking operations. We'll use select to await both of these values simultaneously, printing each one as it arrives. Yeah, I mean, that's what I thought it was. I didn't think it was doing anything different. I'm curious how. So it's always going to be waiting for this number of items. So it's just going to block here until it's got the correct number of items that it wants. And by filling this up, this is like saying, we don't have a value here for you, but we're definitely going to put one in here for you. So you'll have enough, right? So you'll have enough to finish. So if this is waiting on 5 items, we've got to pump in 5 items here so it can exit out. Yeah, that's. I see this pattern a lot with Go, where they have another channel and they fill it up with the size of the pipeline, and it still throws me off every time. It seems like it's unnecessary plumbing for some reason. But this approach has a problem. Each downstream receiver needs to know the number of potentially blocked upstream. Yes, exactly. That's my point. This approach has a problem. Each downstream receiver needs to know the number of potentially blocked upstream senders and arrange to signal those senders on early return. Keeping track of those counts is tedious and error-prone. Exactly. Right. Okay, so I'm not crazy. We need a way to tell an unknown, an unbound number of Go routines to stop sending their values. In Go, we can do this by closing a channel because a receive operation on a closed channel can always process immediately, yielding the element type's 0 value. This means that main can unblock all the senders simply by closing the done channel, and this close is effectively a broadcast signal to all senders. Okay, well, that's better. We extend each of our pipeline functions to accept done as a parameter and arrange for a close to happen with a defer statement so that all return paths for main will signal the pipeline stages to exit. All right. So once we're finished here, we'll defer this close, which will shut down this channel. All this is the same, and we don't have to fill up that pipeline again. So yes, let's do that. Now, in this case, okay, there we go. That's much better. All right, that's what I was looking for. Where's the break? Remember I was saying earlier, where's the break? There's the break right there. So we're going to defer our done once we exit out of this. And if this channel closes, well, or until done is closed, and then calls that. So there was a comment up there that I wanted to see. Yeah, this. We can close the channel because a receive operation on a closed channel can always proceed immediately, yielding the element type's 0 value. So in this case, we don't really care. I want to see this. Receive operator. For of channel type, the value of the receive operation is the value received from the channel. The channel direction must permit receive operations. The expression blocks until the value is available, yielding from a nil channel blocks forever, right? A receive operation on a closed channel can always proceed immediately, yielding the element 0 value. So in this case here, grab this, an untyped Boolean result. Okay. The value of OK is true. The value received is delivered by successful, or false if it is a 0 value generated because the value, there we go. So that's better. So you don't want to depend just on the 0 value for an int, because 0 could be a legitimate value, but having that Boolean there to say that the channel is closed is a better way to go. I don't know if we're doing that in here. I don't think we are. Let's just have a look at that. I don't need these anymore. Yeah, so in this case, we're not paying attention to this. It's funny though. I wonder how that select works with that false value. Because we're not, this is a multi-value return, but in here we're treating it as a single value. Another little quirk of Golang that I'm not a big fan of. And then in square, we need the same thing. Oh, no, we already got that one. Right. Merge, square. Let's see if square has got it. No, it doesn't. So it needs the same deal as well. So we'll just get it from a channel. And it just says struct. I don't think it really makes any difference, does it? Or is it an int? No, it's still, we're keeping it as a struct. It's funny they would use an undefined struct as opposed to like an undefined, well, I suppose it has to be a struct, it can't be an interface. All right, so we'll do another one of those defer closes. So we had to go with the full switch statement in this now instead, because we could have multiple channels that we're dealing with. Right, so if we have something come in on the input channel, then return the square of it. If we get something fail on, or if this channel is closed, then this will get called. Or if there's a value in it. So we'll get both actually. That's still kind of ugly. Sorry. Let's make sure that works. Oh. Right. So square. Move that up. Passing our done in here. close of a closed channel. And that is 31. Right, so this was already closed. I did something wrong here. Square. This is in the square. Okay. Let's make sure our main is the same. Oh, because I don't have it on gen as well. I don't think. Yeah, I need to add it to gen as well. Or do I already have it on gen? I don't think I do. Okay, so let's grab that. And we're going to do a defer close on out. And same sort of deal with the switch here. Just in a bracket. Okay, so we're still getting our close of a closed channel. We'll just find that in a second. Okay, so this example goes on for some other examples here, this blog article, but we're going to stick to this one, figure out why we're getting that close. Let's just have a look here. So let's go down to our main, and we're going to make our closed channel, and eventually we will close that when we're done here, which is, yeah, I don't want that anymore. So in this case, we grab one value, and then the close happens, which will notify merge, right? So merge then, which was waiting for this other one to come through, gets this, and it returns, and the working group is, oh wait, no, maybe I'll get this done twice. I think so. Merge. Oh. That's only supposed to be, oh no, that's right. Oh yeah, so I'm supposed to take that one out. That one's in twice. Don't need that. Okay. So we closed, and then this got notified. So this can bail out. And it said we wanted so many of these. But this could exit early. do one for every value that comes in? Yeah, that's correct. Okay, and then we get up to here. And defer the close on out. And if we get something from here, we bail out. Oh, we have this one here again. So yeah, we've just done 2 closes. Probably got the same problem up here. There we go. Okay, so I had too many closes in there. Okay, good. So that's not so bad. So here are the guidelines for a pipeline construction. Stages close their outbound channels when all the send operations are done. Stages keep receiving values from inbound channels until those values are closed and the senders are unblocked. Pipelines unblock senders either by ensuring there's enough buffer for all the values that are sent or by explicitly signaling senders when the receiver may abandon the channel. Okay, good. Well, you know what? I think that's a good start. But I do want to finish this one. We'll come back to it and get into like digesting a tree and parallel digestion and some of these other little issues here. Bounded parallelism. And go through it. Cool. All right. Thanks, and stay tuned for another part, and we'll go through some more of this with some more Go concurrency. Cheers.